Welcome, everyone. Today, we'll dive into the fascinating world of square-free integers and explore how their density approaches 6 over pi squared. Last time we used Mobius inversion to count primitive necklaces, and earlier we guessed the density of square-free numbers from data.
So today we go back to that square-free pattern and actually prove what the true density is.
The formula on the slide is our main goal. The fraction of numbers up to x that are square-free should settle down to the constant 6 over pi squared. In the previous lecture, Mobius inversion helped us count primitive necklaces, showing how powerful this tool is for separating out primitive structures.
I remember computing that Q of 100 is 61 and Q of 1000 is about 608.
Those values suggested that the ratio Q of x over x hovers near about 0.608 as x grows. Our mission is to turn that guess into a theorem, even getting a precise error term that shrinks like 1 over square root of x. To get there, we will build a clever indicator for square-free numbers and reshape the counting problem into a sum we can analyze. A classic trick in counting problems is to build a 0-1 indicator that fires exactly when the property we care about holds.
So for us, that property is that n is square-free.
Here is the definition. For each integer n, Q of n is the sum of mu of d over all d whose square divides n. We design Q so that it outputs 1 exactly when n has no repeated prime factors, meaning n is square-free.
So for a fixed n, we list every d whose square divides n and add up the corresponding mu of d values.
Because mu takes values 1, -1, or 0 depending on square-free structure, the contributions from numbers with an extra square factor cancel out. If we split n as a square part times a square-free part, we can track how many ways that happens and see that everything collapses to 1 or 0.
So Q really is a perfect yes or no test for square-free numbers, built entirely out of mu values.
Once we have an indicator, counting square-free numbers up to x is just summing that indicator. Here, Q of x, the number of square-free integers up to x, is the sum of Q of n for n up to x. Substituting our formula for Q turns this into a double sum over all pairs n and d, with d squared dividing n.
So instead of thinking directly about square-free numbers, we just add up this indicator Q over all n up to x.
You can picture each contribution as a point with horizontal coordinate d and vertical coordinate n whenever d squared divides n. Because n is at most x, and d squared must be at most n, all these points lie in a finite region of the grid.
So the plan is to rearrange this double sum without worrying about convergence issues, since we only have finitely many terms.
Rewriting this sum by grouping terms by d instead of n will reveal the main term and the error very clearly. Because our double sum has only finitely many terms, we are free to change the order of summation. After swapping, for each fixed d, we count how many n up to x have d squared dividing n, and that count is the floor of x over d squared.
For a chosen d, the multiples of d squared up to x are exactly the n that contribute for that d.
The count of those multiples is the integer part of x divided by d squared, which is shown in the floor function. If d squared is already larger than x, there are no multiples at all, so those d values do not appear in the sum. Since there are only about square root of x different d values, the sum is finite and changing the order does not affect the value.
So now Q of x is a single sum over d, which seems much easier to approximate than the original double sum.
The floor function is close to ordinary division, and the difference will create our error term. We write the floor of x over d squared as the exact quotient plus a small error term epsilon d of x. Substituting this into the formula for Q of x splits it into a main term involving x times a sum over d plus an error sum involving the epsilon terms.
Because the floor is within one of the exact quotient, each epsilon term always stays between -1 and 1.
only d up to square root of x appear at all, so there are on the order of square root of x terms in the error sum. If each term has size at most 1 and there are about square root of x terms, the entire error is at most a constant times square root of x.
Since the main term grows like x, dividing everything by x will make this error shrink like 1 over square root of x.
We now have q of x expressed as a clean main term plus a controlled error, which is the key setup for taking limits. Let us collect our work into a single asymptotic formula for q of x. The main term involves x times the infinite sum of mu of d over d squared, and the entire remainder is bounded by a constant times square root of x. Dividing by x and letting x grow, the error divided by x goes to 0, so the ratio q of x over x tends to this constant, which we know equals 6 over pi squared. Because the series of mu of d over d squared converges absolutely, adding the tail beyond square root of x only changes the main term by a tiny amount.
Once we divide by x, that square root of x error term turns into 1 over square root of x, which goes to 0.
So the proportion of integers up to x that are square free equals 6 over pi squared, up to an error that shrinks like 1 over square root of x.
That matches the decimal pattern we saw earlier, and now we understand exactly how fast it converges.
Let us compare the theorem with some concrete values of q of x. Up to 100, there are 61 square-free numbers, giving a ratio of about 0.61.
For 1,000, we saw there are 608 square-free numbers, and the ratio is already very close to 0.608.
If you push the computation to 100,000, the ratio q of x over x gets extremely close to 0.6079. If you plot the difference between q of x over x and 6 over pi squared, multiplied by square root of x, the values stay roughly bounded, just as the error term predicts.
So the numbers confirm that the theoretical density and the square root error term really describe what happens.
We have proved that the density of square-free numbers equals a certain constant, but where does that constant come from? There is a beautiful identity. The series involving mu turns into a product over all primes, and that connects to the value of the zeta function at 2, which equals 6 over pi squared.
So the proportion of square-free numbers is controlled by this infinite series built from mu.
Euler discovered that sums like this can be turned into products over primes, reflecting how every integer factors uniquely into primes. From the famous Basel problem, we know that the zeta function at 2 is a rational multiple of pi squared, which explains why pi shows up here.
So the next lecture will tie together primes, the zeta function, and square-free numbers into one coherent picture.
The appearance of pi in counting whole numbers is not an accident, and Euler products will show us why. Before we finish, let us check that you are comfortable with how we controlled the error term. This equation summarizes the key estimate. The contribution from the epsilon terms is bounded by a constant times square root of x. For practice, justify this bound. Each epsilon term has size at most 1, and only d up to square root of x appear, so the whole sum cannot exceed a constant times square root of x.
It tells me that if I pick a large integer at random, the chance it is square-free is about 6 over pi squared, a bit more than 60%.
That probabilistic viewpoint is one of the joys of analytic number theory, and it will keep showing up as we explore primes and beyond. Thanks for watching this. Subscribe to Thinking in Math for more topics. We welcome your feedback, leave questions and suggestions in the comments.